We are now continuing the series tunneling in QFT, and as you might be aware of, this series is available on Indico, and also all the talks are recorded and stored on YouTube, so you can go there and check them out. Previous talks include Patrick Draper, Yutaro Shoji, Sylvia Pla, and Ian Moss. So these are talks related to tunneling QFT more broadly. And the upcoming talks are going to be by Wen-Yuan Ai on the 13th of June and Laura Battini on the 11th of July. Today, we have the pleasure of hosting Lorenzo Ubaldi. So Lorenzo Ubaldi is here at the IJS, Standard Track Faculty, and he did his PhD at UC Santa Cruz and postdocs in Bonn, Tel Aviv, Trieste, and Genoa. He's worked on a variety of topics, including astrophysics, cosmology, various VSM studies, and recently he's been investigating topics related to post-vacuum decay together with collaborators. So today he's going to talk about a couple of papers, one very recent and another one a little bit less, which is about post-vacuum decay from thin to thick walls. So please.
Thanks a lot, Miha. Hi, everybody on Zoom and in the room. So this is kind of a hybrid seminar in many ways, because on top of being part of this series, it also became part of a local seminar series. So I try to find some kind of a compromise to make at least part of the talk accessible to the non-experts, and the other part maybe a bit more for the experts. Maybe I completely failed and I would make everybody unhappy. Well, we'll see. So, but I'm happy to take questions at any point. So we'll see how this goes. So there is an audience live in the room here in Ljubljana, and people there. So let me start immediately. So first, Miha already mentioned that what I'm going to talk about is based really on these two papers that I'm listing here, giving their archive number. And this is work done with these amazing people you see here. Alexander Ivanov, Marco Matteini, Miha Nemelshek, Yutaro Shoji, you already know him well from the previous seminar, and myself. So actually a bunch of these people are in the room. So if you ask questions that are too easy, I will let them answer, okay? Good. Click again. Okay, so let's say part for the less experts, maybe in some sense, maybe not, maybe. But anyway, so why is it interesting to study vacuum decay? I mean, it's a few reasons, at least for me. No, there are probably many reasons, but I mean, one is that the electroweak vacuum is possibly, I should add really, but possibly metastable. So it could decay, something that has been studied quite a lot. So that's really has to do with the real world. So the standard model has a vacuum that could be unstable. So you want to understand how to calculate the lifetime. Now, the reason for sure why it is interesting to study vacuum decay is because there are many beyond the standard model models. And in several of them, it is possible to have some scalar field configurations such that you have this kind of vacuum decay. And this leads to possible phase transitions in your universe. These phase transitions could be first order. If that is so, then they could lead to gravitational wave signals. And now we are in the era where we can detect gravitational waves. So if you see a signal like that, you also want to understand, you would like to understand if there is a model behind. And the first step to understand where the signal comes from is understanding really from the theoretical point of view, what describes this vacuum decay, which leads to the phase transition. So that would be the starting point. Another thing to me is just purely academic interest in some sense, because this is a problem in quantum field theory, which is a framework which is clearly well established, that we are supposed to know well inside out. And within this framework, computing the tunneling in field theory is a challenging problem. I will describe aspects of that. So already that for me is also good enough reason. And specifically in this talk, as I put those in the abstract, I will really focus on, let's say, possibly the simplest thing that you can think of, which is a theory with only one real scalar field that has a potential such that there is a false vacuum and true vacuum, so there is decay. And I will only consider flat spacetime, so I will not consider gravity or cosmology for now. So my idea is to go back to the very basics and see how much we can understand, this framework from the very beginning, in the simplest form. So here is what I'm pretty much going to talk about. So you have a scalar field that has some kind of a potential that displays what I call FV, which is the false vacuum, and TV, the true vacuum. So of course, the false vacuum is a local minimum, but the absolute minimum is the true vacuum, the one that is deeper. So if you are in the false vacuum in that VF, you know that classically you will stay there forever. But we're doing quantum field theory, so quantum mechanically, that vacuum will not be stable. So the field will want to go to the lowest energy state. So it will do it somehow, it will time it. So we want to study the formalism to describe this process. And also, keep in mind that let's say the simplest way to write a potential that displays this kind of feature, with these two minima, is something like I wrote, So you write like kind of the usual Mexican arc potential, the phi squared minus v squared, everything squared, and then you add the linear term to tilt it so that the two vacua have different potential energies.
What is delta?
Very good. So delta is a parameter, okay? And it is a dimensionless parameter, the way it's defined there, okay? It's actually, I think we're all used to thinking in 4D, 3+1, in field theory. Delta defined away a very good thing, the property that it has. It is dimensionless in any D, in any spacetime dimensions. So that's good that you asked that question. This is also the potential that Coleman wrote in his first paper when he studied vacuum decay. He called that combination lambda v cube delta, he called it epsilon. So some people might be used to that. We reparameterize that exactly for the reason I told you. It's convenient to have this dimensionless parameter. So good. So now to study vacuum decay, we do this in Euclidean spacetime, not in Minkowski. That's also the way Coleman set up the problem. So this is the action that we write. So there is a plus before the potential, again, because it's Euclidean, okay? Now, what you're interested in is the decay rate of the false vacuum. Decay rate per unit volume. That's what it is. So the V at the denominator is the space volume, space, okay? So in 3+1 dimensions, that's a three-dimensional space. And typically, the way this rate is written is in this form. So E times E to the minus something. So A is a prefactor. I will get to that. And at the exponent, you have this negative bounce action. So the point is, the larger the action, the more is suppressed, the exponent is suppressed, and the slower the rate, okay? Now, usually a lot of people know the common one way this is typically treated in a lot of literature is, look, if I have this form, it's clear that I have to really worry about what goes in the exponent because it's an exponent, so exponential. So A, we can just estimate by naive dimensional analysis. That's typically good enough. But in this talk, I'm going to be way more like pedantic about this. This is also pretty much what we did in those two papers. By the way, I should also mention that I'm talking about two papers that in total are about like 115 pages probably. So I'm not going to do justice on them. And also I apologize because you will see many patients because this thing is quite technical. But again, interrupt me if there is anything which is not clear. So here I will just flash this for now. I will get back to this expression, but this is to say that that's the first line is kind of a, let's say, sloppy way of writing the good enough in some sense. But if you want to be precise, this is the definition. So the way we compute such a decay rate, we do a path integral. So we do quantum field theory using the path integral method. Okay, that's the definition of this. This T is the Euclidean time. So we take the limit in which this time goes to infinity, V is still the volume, and we want to compute this ratio of path integrals. Now I will describe what I mean by phi B and phi Fe. Phi Fe is a false vacuum location. If you do functional methods on path integrals, this probably many people are familiar with, because I'm talking of a scalar field, once I expand so this is an expansion of the action around the stationary point. So phi b as phi of v are stationary points of the action, meaning that the first derivative of the action with respect to the field is equal to 0. That's why the next term in the exponent is the second derivative of the action, okay? We do the path integral over the field phi, okay, that appears there quadratically. So when you do that, the result is a determinant of the operator. And this operator here, for instance, is the one that corresponds to S double prime. Okay, so this is just a functional method, and we'll get back to them. But now, let me again reiterate the fact that it's true to some extent that for sure you can already capture, a lot of physics by understanding the classical action. So S of phi b is a classical Euclidean action. So now I will spend some time talking about that, how we deal with that part, okay? And then I will get back to these other things. So classical bounce action. I rewrote the action here as I wrote before. Now what I'm telling you is that I already mentioned this, that this phi b that I handed in the slide is this field that extremizes the action. So you write the action, you write the equations of motion, and the bounce field is that field configuration that satisfies this equation of motion, which is just derived by varying this action, with these boundary conditions. Now, sorry, I didn't rewrite exactly the other action. Here, what is different is that it was shown already back in the days in 77, sorry, by Coleman and these other two authors, that the configuration which is relevant for tunneling, this field that minimizes the action, enjoys a spherical symmetry. So once they prove that, we can go with that. And so you directly write the action with the spherical symmetry. This is nice because now you go down to only a one-dimensional problem. This is the equation of motion, and those are the boundary conditions. Now, to give you a feeling of what this is, remember I had the potential with the delta linear term tilt, right? So now if you look at the red line here, the red line, the two minima are almost degenerate. That's for small delta, no, small tilt. If I increase delta, I can go to a scenario where I have the blue line, so where the difference in vacuum energy is larger. Now, if you solve this equation of motion for the bounce, what happens is that for the red case, which is what we call thin wall, the solution of this field phi as a function of rho, the Euclidean radius, looks like this. So it's a field that at rho equals 0, you see the phi dot is 0 here, and at rho equals 0, this field is at the true vacuum. And then as you go out in rho space, eventually it reaches the false vacuum. So it matches this boundary condition here. And the way it does this, this is almost a step function, okay? So the variation happens at some radius, okay? And this we would call this radius here, Euclidean radius, we would call the radius of the bubble that you nucleate. Because really what happens in these transitions is that gamma over V describes a nucleation rate. So nucleation rate means that you are nucleating a bubble in space-time here. And the bubble has this profile, meaning that at the center of the bubble, the field configuration is in the true vacuum. Outside, outer in space, my field has the false vacuum valve. And in between, it has to do that transition somehow. If I am in a configuration like the blue one, so where the vacuum energy difference is larger, you see that the transition is not so sharp for phi over rho. So it's something like much smoother like that. And there are a couple of things. Now, at the center of the bubble, I'm not really at the true vacuum. I am at some point which is like between here and the false vacuum. So somewhere here, say, okay? And then still at rho going to infinity, it must reach by the boundary condition of the false vacuum, which now you see it's at a slightly smaller field value, no? So the two figures match. Yes.
This because the barrier is smaller for the red or for the blue?
Yes.
It's broader wall.
Yeah,
Somehow.
it's yeah. So it
Barrier
depends
is
exactly on the
smaller
detail
for-
of the barrier and on. By the way, this is just a cartoon here.
Yeah,
No, it's yeah. But yeah, so the details about this shape goes depends exactly on the vacuum energy difference and on the how high the barrier is and all of that. Right, exactly. But here, what I want to emphasize is that when you go from thin, so again, so if you look at something like this, the reason why we call the red like a thin wall solution is because the wall pretty much is the region where the field value changes, right? So here you see that the region is very small in draw space for the red line. So that's a thin wall. So you think of this bubble, there is a true vacuum. There is a true vacuum inside. and the pulse vacuum outside, and the two regions are separated by a small row space. Whereas for the blue is different, no? Like the wall is thick, meaning that there is a few region, a larger region where this profile changes. So given that my talk is from thin to thick, I wanted to emphasize, okay, this aspect. Good. Oh, still worse, maybe. So now let me talk first about the red line, because so I should also mention, let me go back here for a second. So in principle, this equation here with the potential that I wrote and that I rewrite here, okay, the bounce equation, already for that simple potential, you cannot solve it analytically, okay? So you immediately have to resort to numerical methods even to solve for this bounce profile. It's really, there is no analytic solution, not even for this case, okay? In the standard model there is, but let me, maybe eventually I'll mention that. But just to say that it's really, really hard to, there are very few cases where the bounce equation can be solved analytically. So how can we try to approach this problem analytically? Because we think that analytically we get a better understanding of what is going on. So one way is this. You start from the thin wall regime, which is again the red line. If you have good eyes, you see that this vacuum is slightly lower than the other, here still. So here the thin wall approximation in this parameter is when this delta dimensionless parameter is very small, okay? When it tends to zero. When delta is zero, these two backward degenerate, okay? So now let's study this problem in this approximation. So it is convenient to introduce these dimensionless variables. So z and r are dimensionless, var phi is dimensionless. So this also, in a way, this is also a story of this talk of how to do calculations, in an easier way. It's also very important to choose the right variables and dimensionless variables and whatnot. You can make your life a lot more complicated if you don't pick the right variables. So it was also why it's useful to define delta here. Okay, so good. So again, delta is a small parameter in the game. So now for r, this r is kind of the dimensionless version of the bubble radius. And this is, in a sense, it's an ansatz. You can write this. You don't have to, but you can write this. You can expect that, as I showed you here, now you see that this is a thin wall approximation, the red line, and the radius is large here. For the blue curve, the radius would be somewhere here, so it's a smaller radii. So you can imagine that the smaller you make delta, which means the closer you are to the degenerate vacua, the larger the radius. That's why you have these ansatz, that r goes as 1 over delta, and then you can write a series for them. Also, you can expand the field, the dimensionless field in as a delta series, okay? So now you do this, you plug this into the bounce equation. Your bounce equation, the new variables looks like this. So now derivatives over rho become derivatives over z, right? And this is the new bounce equation. Now, what the new, it's still the same, just with the new variables. And now the strategy is that you solve this order by order in delta, which is r is an expansion in delta, so I plug that in. Phi is also an expansion in delta, so I plug that in. So the first equation that I want to solve is at order delta to the 0. That equation doesn't have the friction term. It doesn't have the delta because that's order delta. So it's the second derivative minus this term equals 0. The solution to that is a hyperbolic tangent. Hyperbolic tangent is something that looks really like this red line that I drew here. Okay, that's zeroth order solution. You solve the zeroth order, you plug it into the delta order version of this equation, and now you solve for order 1. So you find phi 1. And incidentally, you find also r0 at that order. Then you find the solution, you plug it into the next order delta squared, you find phi 2 and r1. You can go on, you plug it into the next order, you find phi 3 and r2, and so on. Now, the more you go, the longer these equations become, the more complicated it is to solve. So analytically, you run out of steam. So what we managed to do analytically is to solve these equations up to order delta squared. That is already quite a lot of work. That is in the first paper that we wrote, part of it. I mean, so there is much more else in that paper. But I just want to outline what the strategy is. Let me also keep track of time. Good. So now more equations.
Wait a second. Yeah. This delta parameter, like here you say, okay, it's much smaller than 1. But,
Yes.
Is this always a perturbative parameter in the sense, like it has an upper limit, or it can be whatever?
Oh no, there is an upper limit. I will get back to that very soon. Okay. It's not a question of perturbativity here. Because, I mean,
Not just that you are able to do this data expansion.
good, exactly. So, can I get back to
Yeah,
this?
sure.
But just maybe to clarify, if this clarifies, no, is that if you have perturbativity in mind, a la QFT, no, meaning I have a parameter, and now if I compute, let's say, loop corrections, no, this is a completely different thing, no? Here is
Of
just,
course.
right.
Yeah.
So that kind of perturbativity is related to lambda here, say, no, the coupling.
No.
But delta, you're saying here small, I just mean that I am in a configuration where the vacua are almost degenerate, and what you're asking is if I increase delta, the difference in vacua increases,
Of course.
and how good is this
You need to
approximation?
go to a higher orders in data.
Exactly. So this is actually one of the main points of this whole talk. So we get to your question in a couple of slides. If I don't answer, ask me again. Good. So, okay. I told you, sorry, I warned you, there are many equations. But now the point is, once you solve like this equation, okay, so now you have your phi and r. Now, what you're interested in, remember, the decay rate went as e to the minus s to the phi b. So that's the object I want to compute. I want to compute the action, which is calculated on this field that extremizes it, right? So by solving the bounce equation, I find that field configuration, which extremizes the action. Now I plug that back into the action to compute the action. So what does the action look like in these dimensionless parameters that I introduced? It looks like this. So omega again is a solid angle. I keep, for now, the discussion generic to these space-time dimensions. I remember we are in Euclidean. So this is this. There are a couple of nice features of this, which is this combination of parameters, v to the 4 minus d and lambda to the d half minus 1, always factors out of the integral. It's there, done. So that's taken care of once and forever. And inside the integral, I have only something which is a function of delta, no? Remember, because my phi is expanding in a delta series, and r is expanded in a delta series. So now, as I wrote above, everything which is inside this integral, I can give it this name, SL of delta. So it's just, it's a number for any delta. Now I have to solve the integral with a proper field configuration. Now, because we found the solutions as a series expansion in delta, it means that now I can also compute this object, SL, which is this integral, as a power series in delta. I just have to plug that in and be careful in tracking all the right delta orders every time, because there are boundary terms, these are here, and the boundary of the integral depends on delta, so you have to do this carefully. But of course, it can be done. No, you do your 10 pages of algebra, blah, blah. More actually, but it's fine. So then you find the solution. So you find that at the leading order in delta, this SL at the leading order, which I call 0, has this form. So the important thing here is that it goes as 1 over delta to d minus 1. So in 4 dimensions, it goes as 1 over delta cubed, for instance. So that's the leading order. And then you find that if you keep, computing, the action goes into this form, where you can factor out this S0 that I wrote here, and then it's a power series of delta with even powers of delta, okay? So again, to compute this, it's really turning the crank, being careful, boundary terms. I mean, there are a few things to be careful about. I say the 10 pages, but actually now here you see, I write this series with these coefficients, which I call S to N with the label N. And here, I say too many equations, but what you see in this slide, to get these two coefficients, especially this one, order 4, it's a good 20 pages probably of pen and paper. It's also kind of long in the appendix. So it's a lot of work, but my main point here that I want to convey is that up to this point, to S4, you can do it analytically. So again, a lot of calculations, but conceptually nothing hard. So that's what you get, okay? Is this so far so good? Good. Now I think I'm gonna get to your question. So
Can you just remind us what is this SL of delta somehow?
very good. So SL of delta is the bounce action, right? Factorizes into the solid angle, this combination of the parameters lambda v that are in the potential.
Basically, what remains.
And only what remains, exactly.
Okay.
Which is also, by the way, what I here. Well, with this notation, what I mean is that this is an SL of delta at order n in the delta expansion. That's the label n there, capital N, right? So this is something that we compute up to the 4th order analytically, okay? And then actually we went up to order 16, n equals 16 numerically, meaning that you do exactly the method that I told you.
So you keep, solving for one order, plugging in into the next, and you keep going. And I told you at order 3, you run out of analytics. You start having huge functions with polylogs and whatnot, so you cannot solve the next order analytic anymore, but you can keep going numerically. So we did, Utaro did a lot of this here. And so I got tired already at order 16, but okay, that happens. And so, but we wanted to check that to see the, how the series converges and whatnot. And now I think this gets to Jonathan's question. So you see, now we have all the corrections to higher order, and the important point is that we are calculating all of this in the small delta limit, no? So we know that we get a better and better approximation of small deltas, and now you can ask, if I use this solution now, in a wide range of delta, so even away from small values close to 0, I go to larger values. Now let me get to how large, it's already in this plot. Do I get a good description of the bounds action, and how do I check that? So as I mentioned at the beginning, all these problems are relatively easily solved numerically. So here, these empty circles and dots that you see are numerical evaluations of the bounds and the bounds action, right? So let's say the dots are the circles and dots are the correct answer because you solve the problem numerically, everything is under control, that's what you get. These dot dashed blue lines are the solution at the leading order. So that would be what I call this S0L. And by the way, parentheses, I should have put maybe also a reference. This is what Coleman computed in his very first paper. No? When he did the thin wall approximation, he stopped here. He said, I do the leading order and he stopped there. So if you do this, that translates into these blue lines. Now, this one is for d equal 4, and this one is for d equal 3. No, you saw it depended on d. So that's the blue line. So now, first point. Of course, this I mentioned also in the abstract. There is a kind of a lore in the literature that say, the only analytic calculation we know of these bounds actions is in the thin wall approximation. But as soon as I depart from thin wall, that is a terrible approximation. It's true. At the leading order, it's like saying this blue line doesn't really go along with these points that are calculated numerically as soon as delta becomes larger than small values, right? So it's true, that's a terrible approximation. Here, though, what is remarkable is that as soon as you start including these corrections that we calculated, the agreement with the numerics is striking. It's actually, we were surprised the first time we plotted this. So you see that even if you go out of this value, there is and by the way, so I labeled this line. So you can barely see the blue here, but the blue is at n equal 4. So including up to this analytic solution. The blue is under the red here. And the green, which is also not visible, it's visible only at the end, is up to n equals 16, which was, as I said, calculated numerically. But so you see that it agrees pretty well. Now, Jonathan, where do we stop with delta? In this parameterization, that's the largest value you can take, delta max, which is 1 over 3 times square root of 3. And the reason is that as you increase delta, the two vacua go farther apart. But also what happens is that the maximum of the barrier moves to the right. The first vacuum moves to the left until they merge into an inflection point. And this inflection point is reached at this value of delta equal to delta max.
An analytic value of delta.
Analytic, yeah. You just solve, you solve what it is, and analytically, that's what you find. Now, if you take delta larger than that, you no longer have an inflection point, you no longer have a minimum. So now you have only an absolute minimum, that stays as a true vacuum, but there's no tunneling anymore because there is no false vacuum anymore. So that's what closes the window of delta in this parameterization, okay? This answers the question, very good. So you see that up to the value, we seem to be doing pretty good, except that, again, we're being very pedantic with many of these things. It looks at these values close to the end. Maybe we could do better. Actually, the red line, that's pretty good. Now, what is this red line? I haven't told you yet what the red line is, which I call n equal 2 cubic to linear. So let me explain that. Now, for Professor Nemelchek's pleasure, I will introduce a much better parameterization for these potentials. No, I'm kidding. So remember, I've been using this potential so far, with this delta. Now, all this is, right, is a potential, polynomial potential up to 5 to the 4th. And what I have is I have a linear term, a quadratic, and a quartic. What you can do, you can always do in field theory, you can just do a field redefinition. So you shift the field by a constant, and you can do it in such a way that you get rid of the linear term, and that introduces a cubic term in the potential. So same physics, I just did a field redefinition, a shape, exactly the same physics, but I changed the parameterization. This turns out, as Professor Neumeyer explains very well, to be a very useful actually parameterization in many situations, and I will show you in a second. So, but first let me do like some notation. So good. So from here you go to something that we parameterize like this. Now we have quadratic, cubic, and quartic. I call this coefficients like that. And now we can again introduce dimensionless variables. Let me stress again that all of these can be done in generically dimensions. And the very nice property of this is that what I call dimensionless is dimensionless in any D. So this is also very useful for the analysis. And now the action again factorizes into something like this. It's similar to what we had before, but with these new parameters. So you see this combination of m and eta, and now this integral is only a function of this parameter that I call epsilon alpha. Okay. And once you do all of this, you find very quickly that what I call v tilde here, which is also a dimensionless version of the potential, has this form. Okay. Now, there are a few interesting things happening here. One is that this is a relatively simple problem in a sense. You have a polynomial up to 5 to the 4th, so you know exactly what kind of shift you have to do. And that means that you have a one-to-one map between these two parameterizations. So between the parameters lambda, v, and delta, and the parameters m, eta, and epsilon alpha. And this is an exact map. It's related by cubic solution to cubic equations, really. That's what it is. So it doesn't look, it looks a bit ugly, but it's analytic, it's exact. So that's something that helps us in many cases, okay? So here is to give you a picture now of what is going on. So on the left, we have, again, the linear parameterization. This is Jonathan also what I would say, delta equals 0, thin wall, degenerate vacua, delta mass, you reach the inflection point in this potential. In the other parameterization, which I rewrote there for your convenience, say, you see, I mean, first of all, if you look at epsilon alpha equals 0, that corresponds exactly to what in the linear would delta equals 0. You see, indeed, the shape is exactly the same for the potential. The only thing that happened is that I shifted the field by 1 unit in dimensionless variable. So here the first vacuum was at 1, here the first vacuum is at 0. So everything is shifted towards the left, right? That's really a field shift. Now, if I move in the space of this epsilon alpha, though, I can go now different directions. Of parameter space, meaning that you see that epsilon alpha equals 0, well, you have to trust me that that's the shape that you get, or you can do the exercise for your figure. If I put epsilon alpha to 1, there's no quartic anymore. And then what happens is this. So the cubic dominates a positive field value, so this keeps going up to infinity, but the negative field values I go to minus infinity when epsilon is equal to 1. So here is a configuration that I would call even like a thicker wall compared to this one, because difference in vacuum energy now becomes even infinite in that sense. So let's study what happens with this parameterization. We don't have to do much now analytically, and the reason is that because of all the work we did with the other parameterization and the fact that we have an exact map, we can take the results we had for the other action and translate using the map. So it's done. So once we translate, we expand in epsilon alpha. That's it. We get this for free. So we get this expansion now in epsilon alpha. So it's very similar to what I had before. So now I'm still looking at the bounds action with this other parameter. The SC0 is really exactly as it was before, with the difference that instead of delta, you have epsilon alpha. But same power, behavior, everything. No. What changes now is that if you remember, for delta, we only had even powers in the expansion. In the epsilon alpha parameterization, we have all of them, even and odd, we have everything. But still, you get that very quickly and analytically. Now, I'm doing all of this to also get back to explain the red line that was in that plot. Now, the point is that the action is really a physical object, doesn't care about what parameterization you use. So this equality must be true. So I can write it either like this or like that. Must be true. So now, this is the map that we use. These fm squared and f eta are functions that again involve cubic square root, whatever. No, they are somewhat complicated, but not too much. But the properties that they are important here is that fm squared, when delta goes to delta max, this function fm squared goes to 0, as it should be, because if you think about it, m squared, then now parameterizes this potential here. the inflection point in this potential, remember, what is the inflection point? The inflection point is the point where the second derivative also vanishes, both first and second. To make that happen, m squared has to be 0. So the inflection point in this parameterization is described by m squared equal to 0. This is, of course, correctly taken care automatically from the exact map, by what I just told you. So you can already imagine that this map is buying us something. Now this knows that when I go to delta max, this is an inflection point and the action will vanish. Because remember, you see the action is proportional to m, right? So now, by equating these two sides here, I get that SL I can express like this, and now I use the map to write everything as a function of delta, right? So now the name of the game is that I have this action as an expansion in epsilon alpha, okay, which I know how to compute analytically at least up to order 4, and numerically again up to order 16. So I start from that object, and now I use this equation. Once I have that object, I simply use the exact map to translate from the epsilon alpha parameter to delta, and to translate the other parameters into delta. And this is the equation that I get, okay? So all of this I do analytically. So now I get this SL. This SL delta, let me go back a second, is the one here with the red line when I do all that procedure. Now you see this red line seems to do very good with these points. But let me show you, so in this problem, you see here I have a linear scale on the delta axis. So let me show you something that is even more dramatic. So this is the same plot where I change the x-axis. So instead of plotting linearly in delta, I plot logarithmically this combination. So when I plot this combination, now you have to look at this the other way around. But to help you, I put where is the inflection point, where is the degenerate vacua. So it's the other plot looked on a logarithmic scale. So you see there is excellent agreement. Then there seems to be very good agreement also with n equal 4 and n equal 16 of the linear parameterization. On this plot, you see that when you get very, very close to the inflection point, which is on this side, that agreement deteriorates quite a lot. But remarkably, at least to me, if I do the procedure I just described, so I start from the cubic, I translate into the linear, I cut at second order, actually in the expansion of the cubic, and then I do the translation. Amazing agreement. So to me, this is somewhat remarkable. Now, what we're saying now here again is that we started with a thin wall calculation. So let's remember this, right? We did a calculation which is valid in the regime where epsilon alpha and or delta are small, they're close to 0, right? And then we found the result and we checked, does this result describe correctly also a regime where these epsilon alpha or delta are not really 0, but they're close to much larger values? And the answer is remarkably, it does. Very well. And again, look how much better this does compared to the leading order again with dashed, no? So this is a significant improvement. Good. Now we can also ask, how does all of this do directly the cubic parameterization? So now let me look at the other potential. You can see it more or less here. The degenerate minima is the same form. But now forget about delta, lambda, and v. I'm doing everything in the space of m eta and epsilon alpha, okay? So now I move epsilon alpha from 0 to 1. When epsilon alpha is 1, again, we have the situation with the unbounded potential, right? So you see it here, very small. So it goes up to infinity to positive field values and to negative infinity. False vacuum is at the origin, so I tunnel to the left. But this I should have also stressed, which is to me, well, not very funny, but somewhat ironic. In the web page that we have for this series, there is a figure with a cartoon of the potential with a true vacuum to the right of the false vacuum. That looks wrong to me. I mean, you always want to tunnel to the left, okay? So in all my talk, you always tunnel to the left. You never tunnel to the right. So keep that in mind. We always tunnel to the left. So that's what it is. But good. So this is a plot for three-dimensional field theory. Now we're all like in the cubic parameterization. So this capital N, they count the order in the epsilon alpha expansion of the bound traction, okay? Again, dots are the numerics. This is the thin wall approximation. Here you also see that the numerics depart very quickly from the thin wall. But what you see is that if I take my expansion and I truncate it a second order, which we have analytically, that's the closest, the better approximation to the actual value, which is the numerical value, okay? If you keep including higher orders, it doesn't work anymore. A fancy way of saying this is that the series that we have computed, you should think of as an asymptotic series. So the radius of convergence, you at the beginning, you don't know what it is. From this plot, it seems to indicate that the radius of convergence is probably 0 radius of convergence. So you get a better approximation if you find the optimal point of truncation for the series to approximate what we want to approximate. And what we see is that the optimal truncation is second order here. In d equal 4, second order does even better. So it is the same version of the plot, but in d equal 4. Also, by the way, if you go all the way to n is equal 16, it becomes much worse, which again signals what I just said. I mean, the series, you don't do better by including higher order, simply because if the radius of convergence doesn't cover this range, you're not going to gain much.
What about n equal 1?
N equal 1, I should have plotted, it doesn't do so well. It does worse, I think, even than n equal 5 on this plot, but I should recheck. For sure, n equal 2 is the one that does the best. Good. So again, I feel, again, in my mind, it's somewhat remarkable, no, that let me stress that again, no, common law, like you take the thin wall action that no, everybody knows how to compute. Well, of course, Mr. Coleman told us how to do it. And then you say, I mean, that's the only thing I know how to compute analytically, but if I want to use this analytic result to compute actions where the vacua are not really degenerate, do I get a good result? And the answer is no, it's terrible. As soon as you depart from the thin wall regime, this doesn't approximate anything well anymore. But what we have showed is that if you do these several pages of algebras to compute the corrections in this thin wall parameter, very quickly you reach a remarkable agreement even in these regimes that are clearly far away from thin wall. Okay? Good. By the way, also on Zoom, if you have any question, ask anytime. Huh? I think on time I'm doing okay. So now let's do something insane, okay? I reload the potential for you. In this class, remember, I always stop at epsilon alpha equal 1. Now, let's go crazy. Let's push epsilon alpha beyond 1, okay, larger than 1. If you do that, this vortex goes negative. And now what happens is that the potential is completely unbounded on either side. So this is the purple line. You see, for instance, purple line is an example for epsilon alpha equal 3, right? So potential is completely unbounded. I still have a local minimum at the origin. You see from this plot, you can see, but you see that there is still a barrier, small barrier on the left, and there is definitely much higher barrier on the right. So in this situation, you can tunnel also to the right, but very little because there is much higher barrier to overcome. So let's forget about that. Let's keep thinking about tunneling to the left. That's the only thing we want to think about. So you can see that, I mean, there's nothing so special in that sense now. If I push epsilon alpha to larger values, it goes down steeper, no? But I still have a minimum, a barrier. So let's compute the bounce action in this case, which we can classically. And still, all of this is a classical bounce action. So you do the calculation. This is the result. Again, empty circles and dots are numerical results. The red line is again our thin wall result, okay, truncated at n equal 2. And the full line is for d equal 4, the plain red line is for d equal 4, the dashed red line is for d equal 3. So d equal 3, you see that when I go above epsilon alpha equals 1, it starts deteriorating. It's not too bad actually, because now the scale is logarithmic on this plot. So we're talking, you know, I mean, fine, I mean, it's some difference, but we're talking about the difference between 0.2 and almost 1. So I would have expected much worse. Remember that the action I'm using is calculated in the thin wall approximation. So in a regime which is so far away from what I'm looking at here. And one thing which is now very remarkable, you know that, let me go back here. If I keep cranking up, no, this epsilon alpha to positive values, no, and larger, these terms become more and more negative. It's a quartic term. And at some point, it makes sense to think that this is clearly the dominant term, and they can neglect the other two. Pi squared and pi cubed. No, this makes sense. Would you agree? So when that happens, so for large enough epsilon alpha, I have a theory which classically this would be scale invariant in d equal 4, no? Because I have the 5/4 operator in d equal 4. For that theory, there is a much easier solution for the bounds now. So to solve the bounds equation, that solution is called Fubini-Lipatov. I will show that in a second what it is, and it's in a parameterization. But here I just want to show you that, as expected, when I go to large epsilon alpha, you see this Fubini-Lipatov solution, which is the blue line, is a very good approximation to the data. Well, to the correct values, to the points, numerical points. But it's almost indistinguishable from our line. So now, I mean, at least to me, this is insane. It's insane because, again, Fubini-Lipatov is calculated in the limit of large epsilon alpha, so where I have a very large and negative quartic, and everything else I can neglect. And this is a situation where I have an unbounded potential, where this goes down very steeply, no? So I cannot think of anything thicker than that, okay? This is the thickest I can think of in this model. And now I compare that to our calculation, which we did in the thin wall. So when the two vacua degenerate, no? We have a solution, we use the solution, and that solution is the red line, and that also works amazingly all the way out there. And I'm not cheating, huh? If you don't trust me, just redo this calculation and check it. Really, there's no cheating. So to me, it's remarkable. So why is this working? No? And also it's important, crucial, that we truncate at n equal 2. It was, as you saw in the previous plot, that was also clearly the best truncation point. But remarkably, this keeps working all the way out there. So analytically, there is a reason why that is, and the reason is here. So if you do Fubini-Lipatov and you translate into our notation, blah, blah, no? So the bounce is known, the bounce action is also known. This is exact, this equality here, 8/3 times that factor. So for large epsilon alpha, you can neglect the -1 at the denominator. That's what it looks like, okay? Fubini-Lipatov, the bounce action for Fubini-Lipatov. Thick wall, okay? Our thin wall expansion, truncated epsilon alpha equals 2. If I plug in, those ugly expressions that I showed you for the coefficient in the expansion of the action, in d equal 4, they simplify to these values, okay? So it's still analytic, huh? I want to stress that. So that is the expansion. And you see this 8/3 epsilon alpha, this is 1/6 epsilon alpha times this factor. It's probably just a coincidence, but these two factors are just order one with the other, as you see in the previous plot. And also here, what you see is that, of course, if I stopped at this order, this wouldn't work. If I kept higher order, it also wouldn't work. Because to match Fubini-Lipatov, I need something that goes as 1/epsilon alpha. So it's really crucial, given the structure of the thin wall calculation that we had, that we truncate the expansion of epsilon alpha squared. So somehow this works unbelievably well, no, in this huge regime. So I hope that at least with this, I made justice to the title, not to say that we did a calculation in the thin wall, and we find that we get an analytic answer that covers, at least for this class of potentials, it covers everything. So, good. So let me go here. We have to be brief. Sorry, how much time do I have? 5 minutes, 10?
Well, it's 10 minutes to 3. So maybe 7 minutes.
Good, good. I can do this in 7 minutes because it's the hard part and nobody will know. It's fine. Ooh. Good. So, fluctuations. Okay. So as I tried to stress at the beginning, maybe I didn't stress it enough. What I showed you so far was the calculation, was all classical calculations. Bounce action, classical fields, everything classical. But really, it's never probably enough to stress this point. Vacuum decay is a quantum process. So it really happens because there are quantum effects. Classically, nothing happens. So really, to do justice to this business, you really have to compute this object. So now what I'm showing up here are Feynman diagrams, because in terms of the path integral, if you look at this term, in the path integral, the second order expansion with the second derivative of the action and phi, what this means in terms of Feynman integrals is that I have to do a one loop calculation to compute this object here. And the one loop calculation in terms of Feynman diagrams looks like this. So I have an external field, and I put a cross to indicate that it's a classical background, so it's like a VEV, except that this is not a VEV, because it's not a VEV which is constant over space-time. It's a field that has a profile over rho, which means that, as usual, when we do Feynman diagrams, we do them in momentum space, right? But if I have a field that depends on space-time, then the momentum that flows also into the loop is highly non-trivial. So now when I do this calculation in Feynman diagrams, when I do the loop, it's not a d4k of an easy object. It's a d4k integral of something which has a non-trivial dependence on the external momentum, because the background is not constant, okay? So if you try to do this calculation, which you could try to solve this problem here on the path integral, good luck. I don't think, I mean, in general, for instance, for the potential that I showed you, you cannot even think about doing this analytically. It's super complicated. So you need to resort to different methods. But here, what I want to emphasize is that technically, this part here of the action corresponds to this calculation. And what is nice about Feynman diagrams is that we're used to that, and we see the structure of the divergences. So here, this you can see from these diagrams, because you see, for instance, let's put ourselves in d equal 4. Now, if I have to compute the series of diagrams, and as you could imagine how the series continues, you just put more and more insertions of the external field, right? So now here it means I have one scalar propagator. In field theory, the one scalar propagator is clearly a quadratic divergence in d equal 4. In this diagram, I have two propagators. This is a logarithmic divergence in d equal 4. This diagram is finite in d equal 4 already, right? If I were to do d equal 3, this would be a linear divergence. This would be finite already. If I were to do d equal 2, this would be a log divergence. Second diagram is already finite, and so on, right? So with this, I already see that I'm doing a calculation. It's a QFT calculation. One loop, there are UV divergences. And looking at this diagram, I already know immediately what degree of divergence I have, depending on the dimensions. Now, as I said, it's really hard to do the calculation with Feynman diagrams, so a much better way of doing it is by using functional methods. So by really computing, solving the path integral first, you get in this ratio of determinants, and let's compute the determinants, okay? So that's what we're going to do. Another thing which is important is that what I talked about in the first part of the talk was the classical bounce action. Now, because I'm doing the one loop theory, that's not enough, so I have to do the one loop corrections also to the bounce action, okay? So it means that the couplings at the enter now, they have to be renormalized at one loop. I will have one loop counter terms. That's what the one stands for there, no? But this is really a textbook calculation that you can do with it. So for instance, in the model that I showed you, no, with the quartic potential, that's, if you do the calculation, that's what you find in dimensional regularization. So you compute the one loop structure of the theory. You see that the quartic runs with the log mu, and you can compute the counter terms, and then in red, they have the 1 over epsilon pole structure, okay? So now, we have to put together this together with the functional determinant. The functional determinant corresponds to this calculation up here. So also up here, there will be 1 over epsilon poles in the red. There will be log mu's, right? Because I'm doing it in red. And it better be that the 1 over epsilon pole and log mu terms that I find in the functional determinant will cancel exactly against this, because my finite answer is an observable gamma over mu. So it cannot depend on the regularization scheme. It shouldn't depend on the arbitrary scale mu, okay? And they do cancel. So we checked all of this very explicitly. So I think my 7 minutes are almost up. So here I can go quickly. So you can write this functional determinant in this form. So L is like the multiple. Now think of the hydrogen atom. Remember that we have spherical symmetry in this problem, as I mentioned at the beginning. So you can decompose these functional determinants using the spherical symmetry. And this L is the multiple. So these operators here. So this operator, this Laplacian here times plus this potential becomes this operator using spherical symmetry. L is the orbital quantum number, orbital momentum quantum number, and this is in generic d dimensions still. Let me introduce this label nu. It's just for convenience. It still tracks the multiples, but it's better to keep track of all of this in generic d dimensions. So now we use a powerful theorem, which says something like this. So let me take the log of this determinant, the ratio of the determinant. This log can be written in this form, where these are nu is defined this way. And these functions size are the functions that obey these differential equations. Now, O nu is OL, except that I traded L for mu again, but it's the same operator, okay? So these functions obey these equations with boundary conditions that I didn't bother writing. That's not so important. What is important here is the following. When you compute a determinant, of course, the obvious way is you compute the eigenvalues. Computing the eigenvalues for this problem is very hard, because this operator is too complicated. This Gelfand-Diagonal theorem gets around that, and the reason is that, look, I mean, what I really need is this object. So it's the product of all these determinants. And, or said in another way, like it's the product of all the eigenvalues for each determinant. But what I need to know is the product of the eigenvalues. I don't care about knowing every single eigenvalue. This theorem gets you exactly around that. It's a theorem that does this trick for you, and you can solve this. This is not an eigenvalue equation anymore. Now I set the eigenvalue to 0. So if I solve this equation, I don't find the eigenvalues, but this gives me the product of the eigenvalues and the determinant. It's a theorem. I'm not going to go deeper into that. So that's what we do. Okay. So that's the way we attack this problem. And let me mention a couple of features of this. So first of all, at L equals 0, the eigenvalue is negative. This, by the way, what this means is that, remember that I'm solving the eigenvalues for the second derivative of the action. And the action evaluated at the bounds, and the bounds extremize the action. If there is a negative eigenvalue, this means that this extremum is not a minimum or a maximum, but it is a saddle point. Because when I compute the second derivative of that operator, I have one negative eigenvalue. I will stop very soon. 4 zero eigenvalues, and everything else is positive. So it is a saddle point. So you can take into account all of this. Let me just conclude very quickly. I really have only one slide left. By saying this, because this really is what I was saying before. Now, in this language, first of all, we're doing everything in coordinate space, not in momentum space, as you are used to with Feynman diagrams. But in this language, if you compute what this function is, no, it turns out that it always really has this form. So this first factor, the nu to the d minus 2, is related to the d nu, which is the degeneracy factor for each multiple. And it has this form. And this function log r nu always has this form, meaning that it starts with the 1 over nu term, the next is 1 over nu cube, 1 over nu to the fifth, and so on. So from this, again, you can read out the UV divergences. So now the UV divergences in this language, they don't show up at large momenta, they're still UV divergences, they show up at large multiples. So when nu goes to infinity, for instance, d equals 4, this is nu squared over nu, sum over nu, the first term, that's a quadratically divergent piece. Second piece is nu squared over nu cube is 1 over nu, sum over 1 over nu is a log. So that's the logarithmic divergent piece. So if you do this quick math in your head, now you see immediately that the structure of these divergences is in one-to-one correspondence to the Feynman diagrams that I showed before. So this encodes correctly what this is. Now you have to regularize because of these divergences. So you have to subtract pieces. There are papers on how to do this, which actually we're heavily working on this stuff even right now, but I have no time to say anything about this. So just take this as a prescription. Here you see there is this object I tilde. This contains the 1 over epsilon of mu I told you before. This enters in the functional determinant. These pieces will cancel out exactly against the others that I wrote for the action. And then let's see. So now this is the result. Once you compute those sums, now I call this sigma 4. This is again the sigma 4, and this is what I plot here is epsilon alpha q times sigma 4. Again, like thin wall analytics. Oh, we computed the thin wall analytics in the 2022 paper. That's a very long and hard calculation. This is the result here. And now everything else here is done numerically. So we compute these functional determinants using BubbleDet, which is a very nice software that some of the people on Zoom actually have made available recently. And also it's nice to see this agreement. I even have another anecdote about this, so you should ask me about it as soon as I'm done. Once you compute it numerically, you can fit it. We anchor the fit, you see, I mean, this is clearly log pi. These are analytic results that we obtain in the thin wall, no? And then everything else is described by these functions. Good, so now you can put everything together, and this is my summary. Just to conclude very briefly, now, what I would say is if you want to compute like tunneling from thin to thick wall, everything, including the prefactor, you never have to run numerics ever again, only for this specific potential for only a scalar. Meaning that what I showed you, let me know, we'll sell this. No, but it's just to say that we did all the checks. We have many more checks also in the paper. That if you take this theory, so it's really specific to a theory with a single scalar like this. This is the decay rate, and this is really the full decay rate, one loop including everything, the one loop corrections, everything. And you can put all of these into very simple forms like this, both for the functional determinant and the bounds action. And what I'm telling you is, if you use this recipe here, whether you are in the thin wall or in the thick wall, you get an answer which is a very, very good approximation. So that can save you some time. Sorry for being a bit long. I will stop here. Thank you. Under 1 hour.
Thank you, Lorenzo. Yeah, you started a bit late. So do we have some questions, either from the Zoom audience? Yeah, go ahead, Ollie. Please unmute yourself.
Hi. Yeah, thanks for the talk. So yeah, I had a couple of questions. One, so you mentioned this is specific to this potential, the calculation that you've done. So this thin wall calculation at leading order, can be generalized in that you can write the answer in terms of an integral over the potential, or somehow you can write the answer in terms of the surface tension. So and the difference in the potential energy between the two minima.
Yes.
Do you think something like that could be generalized so that you could write this higher order result in terms of a surface tension, maybe some other quantity which arises at higher orders, and then it could be applicable to more general potentials and even the multi-field case, because this surface tension result also applies to multi-fields.
Exactly. So that's a good question. I don't know if it can easily be generalized there. Possibly, yes. I mean, in principle, yes. No, because you're saying, so you give me a potential. I mean, the first thing would be to identify, if you give me a generic potential, maybe a nice way of parameterizing it such that I have an obvious parameter and hopefully only one, which parameterizes what I mean by thin wall. So I think if I can do that, then in principle, yeah, the rest somehow could go through. But I haven't thought about this, but I think in principle this could be done. Only with a scalar potential. Also, I think, Oliver, to make sure I understand your question, you're only for now asking about the classical bounce action, no? So to compute something as a series expansion, because if we start talking also about the functional determinant, then of course it becomes way messier. But if you're asking only about the classical bounce action, probably in principle, yes. Also, by the way, let's say there was also a paper recently by Jose Espinosa, where he uses his formalism, with tunneling potentials. And I think the title of the paper is really also something like from thin to thick walls. And he shows exactly using this language, the surface tension and whatnot, that you can see, and that's generic, that doesn't refer to any specific potential. It refers to the fact that you can think of the bounce action for the thick wall configuration as like layer over layer over layer of the thin wall result. And it shows that he gets something that makes sense. So maybe in a sense, he already gave us an answer. So maybe if you're only interested in the bounce action for a generic potential, that could be the way to go. I mean, for sure, in his formalism, he showed it. It's really only one page, very nice and clean. So that's an option. I think for us, the reason why we went down this road is because then we could use exactly the same parameter also for the functional determinant, which is a completely different beast and much harder to do. I don't know if I answered your question.
Yeah. I think anyway, you've picked a renormalizable potential. So with one field, there aren't so many of them.
Yeah, right. Mm-hmm.
So there, thanks.
Thanks. Borut, can you?
Yeah, hi. This parameterization of the action, I remember there was a paper from Sarit in like 25 years ago, and he also parameterized the action in the way similar to you did, but of course, have you compared the?
Oh yes, we have. Indeed, actually, I wanted to put Sarit's plot also on my slides. In the end,
sorry,
yeah.
I missed that.
No, I didn't. I say that when I was preparing the slides, I don't know if everybody else was probably not in this audience, but on Zoom, maybe many people are. But Borut is referring to a paper, I think it's 1998, probably, if I remember correctly, or something like that. So it's a single author paper by this guy whose last name is Sarid. And yeah, so he uses exactly the same parameterization that you see in this slide, up to factors of 2 and different labeling, He exactly uses that. And what he does, so a couple of things. First, he doesn't do, also shame on me, I really should have put the citation explicitly on the slides. What do I want to say? Okay, so what he does is only the classical bounce action, right? And what he does is he computes it numerically with this parameterization in the whole range, the one I also showed, from let's say thin wall all the way to completely unbounded potential, where you go all the way to Hubini-Lipatov. And indeed, also Greg in his plot, he shows like a version of the plot I showed, like in a different way, which is that if you have the leading order thin wall approximation, then very quickly doesn't approximate the correct numerical value of the bounce action. So that he already did in this language. But what I'm saying, well, what he did was he did the numerics, okay? And the other thing he did, he says, once I have my answer for the numerics, now I'm gonna fit the numerics, okay? And he also showed that up to the region where the potential is bounded, so in the language that I'm using here, in our notation, this would be in the range of epsilon alpha between 0 and 1. So he showed that in that range, you can parameterize your result of the bounce action as a polynomial in the parameter that we call epsilon alpha. So sorry, this is another important, well, I don't know if it's important, but for instance, Borut also in that direction, no? So he writes as a fit to his numerical result something like our S4 here, right? Except that the coefficients we have here in S4, we compute analytically. The ones he has are a numerical fit, no? Indeed, actually, in the plots I showed, no, I also show like a black line to go to the numerical points. That black line is taken pretty much from his fit. So yes. So I made the answer very long, but yeah, it's.
No, thanks.
Thank you. Any more questions? Okay, no room, no Zoom. Okay, everybody happy? Good, so let's thank Lorenzo again, and we'll see you next time.
Thank you.